All right, let's talk about what happens to a distribution function when you pass it through a strictly increasing differentiable function, or a strictly increasing function which is differentiable on a certain region. Um, so let's see here. So what do we know? So let's just start with things that we know. So since the measure of all points omega such that x of omega is between a and b is equal to 1, we have this by assumption. We also know that p is it's a probability measure, so the measure of the entire space omega is 1, and so it must be the case that the measure of all points where x is less than a is the same as the measure of the points where x is greater than b, which is equal to 0. Okay. Now, since f is the continuous density function f is continuous, the probability that or the measure of x, we'll just call it the probability that x equals some lowercase x is, well, we know, let's see here, we proved a thing that's this is f of x minus f of x minus, where x minus is a limit as y approaches x from the left of f of y. However, by the continuity of lowercase f, we know that there are there's no jumps in the density function f, and so this f of x minus is equal to f of x. So this is just f of x minus f of x equals 0 for all numbers x. And thus, we know that the probability of x is less than or equal to a is equal to the probability that x is greater than or equal to a, or greater than or equal to beta, which is equal to 0. And we know this because the probability that x is less than or equal to alpha, I meant to say alpha instead of a, it's equal to the probability that x is strictly less than alpha plus the probability that x is equal to alpha. And that's just from additivity of measure functions, or measures. Okay, so we know this. And so basically, so let h of y be, so we have indicator function on the interval g of alpha, g of beta. This indicator function times f of g inverse y over g prime g inverse y. So this is precisely the density function that we want to prove that g of x has. And indeed, this function, let's see here, if y is in this open interval, then it has this form, this thing that I've written down, and it's 0 otherwise, which is why I added in the indicator function there. Okay, so we want to prove that the probability that g of x is less than or equal to x equals the integral from negative infinity to x of h of y dy. And we're already sort of part of the way there, because certainly the probability that g of x is less than or equal to let's see here, the probability that g of x is less than or equal to g of alpha is the same as here. Let's actually write this. I'm actually going to write this out. So, since g is strictly increasing, I'll just write this. x of y, well, this is really x of omega, is less than or equal to x if and only if g of x of omega is less than or equal to g of x. And that's just true of increasing functions because, wait, let me think about this. Right, because it's increasing, so x is greater than or equal to x of omega, so when you put it in, it's going to be larger. Okay, so the probability that g of x is less than or equal to g of alpha is precisely the same as the probability that g of x is greater than or equal to g of beta. These are both equal to 0. Right? Because you just get rid of the g's, and then you are back to the probability of x being less than or equal to alpha and the probability of x being greater than or equal to beta. And so this actually matches with how the density function h should behave. If h is the density function for g of x, then it should behave like this because it needs to be 0 when you're below g of alpha and when you're above g of beta, and it is. Okay. Alright, so now let's do a little bit more work. This is just a preliminary thing. Since g is strictly increasing, it is 1 to 1, so it is, in particular, invertible. So let a and b, these are going to be real numbers because g is assumed to be a real function. I guess it doesn't specify it, but for g to be strictly increasing and differentiable, that means that that implies that g has to be a function from r to r. So a and b are real numbers such that g of alpha is strictly less than a, is strictly less than b, is strictly less than g of beta. Then, if we consider the set where g of x is between a and b, then this, we can just take g inverse of everything because g is invertible. When we take g inverse of g of x, we're going to get just x. Sometimes when you're doing that, if you're doing it in terms of sets, then you need to be careful about inclusions. But here we're actually assuming that, or we've actually shown that g has an inverse. And so we don't really need to worry about set inclusions. Because in general, the inverse image of a set is, I forget off the top of my head. It's either contained in the set or it contains the set. There's inclusion in one direction, which is true always, even for functions which are not invertible. And there you just let the inverse function just denote the set of all points which map to a certain set. But anyways, because we have invertible or invertibility, these two are, actually these should be the same. So I was right when I was writing that the first time. Okay, so we have this, if and only if this. So, let's continue. So, now let's try to compute the probability that g of x is between a and b. Well, we want to write this in terms of something which we can compute, which is probabilities involving x. So this is the same as the probability that g inverse of a is less than or equal to x, which is less than or equal to g inverse of b. And because we have a density function, we can just write this as the integral from g inverse a to g inverse b of f of y dy. Okay, so now in order to compute this integral, so we needed g to be strictly increasing, so that first of all, so that we could invert it, but second of all, so that we could get the relationship between let's see, the first thing over here where I brought it up. So that's when we needed it to be strictly increasing. And the other thing we know is that it's differentiable. And now we're going to use that because in order to, we can actually figure out what this integral is, or write a formula for this integral, and we want to use a u substitution. And we're going to let u equal g of y. Alright, so then du equals g prime of y dy, which works because g prime is, or since g is differentiable. But then we also need some other facts that will allow us to substitute this variable u in more easily. So if we solve in terms of y, we have g inverse u equals y, just solving for y in the first equation. And now substituting this into the second equation gives us, let's see here, so we have dy is just du over g prime of g inverse y. And so now at this point you should sort of see, like, let's see here, so we define this function h, and we had these weird things in there like f of g inverse divided by g prime of g inverse, and where are these things coming from? And it's, you can see here that they're coming from this change of variables. Okay, so now that we have this, then we have that the probability that a is less than or equal to g of x is less than or equal to b. Well, we already got this integral formula for it, but now we can make the substitution. So we have to change the bounds of the integral. So first we have to, let's see here, so when y equals g inverse of a, u is g of g inverse of a, which is a. And similarly, the upper bound will be b. And then instead of f of y, we have f of, let's see here, so y is g inverse of u, so f of g inverse of u. And then we have to multiply, we have to replace dy with du over g prime g inverse. And I'll just put g prime g inverse right here. This should be g prime g inverse of u, not y. And then this whole thing du. And then this is precisely the integral from a to b of h of y dy. I guess technically here it would be h of u du, but at this point the variable doesn't really matter all that much. Okay. So, now finally, since h vanishes outside of the interval from g alpha to g of beta, we have what? The probability that g of x is less than or equal to x is equal to, well, let's see here. So this is going to be the integral from negative infinity to g of x of well, actually, here, I'm just going to write out what it ends up being. It's just, all we end up with is the integral from negative infinity to x of h of y dy. Because what happens is that if x is less than g of alpha, then you're just you have 0, which is exactly what happens because h vanishes there. If x is between g alpha and g beta, then you integrate from negative infinity to g alpha, and that's going to give you 0. But then you add the integral from g alpha to x, which matches with the support of h. And then if x happens to be beyond g beta, then you just have 1. And so yeah, that's it. So yeah, this proof, I feel like this proof isn't like entirely streamlined. There were a few, like this gives like the basic idea of all the ingredients that are required for this proof. I'm not sure if it's organized as well as it could be, but this is basically everything that you need in order to solve this exercise. And there is another thing at the very end of the statement or end of the exercise that tells you what happens when g is a linear function with positive slope, and that's all just immediate corollaries of this result that we've proven. So yeah, this sort of gives you a way to transform probability distributions. And that's what we were asked to do in this exercise. So now we are done.